understanding and using lithium rechargeable batteries. Our guest speaker today is Simon Chan, the Chief Engineer of Radlink Communications. We are recording the session, so you will receive a copy of this session plus a copy of the slides in about 2 weeks' time. We like to make this session as interactive as possible, so if you have any questions at all, please feel free to put them in the text box. If you have a microphone, then I'm sure we can have a question and answer session at the end, or maybe Simon may hand the microphone over to you partway through. My name's Carol Moverley. I'm based in the IDC and EIT office in the UK, and I'm going to pass over to Simon, who's based in Perth in Western Australia. I have started the recording, Simon, so over to you now.
Hello and welcome everyone to this webinar. It's a bit of a different experience for me to address you invisibly, so to speak, but I'm glad that you're with us, and I can see that there is quite a number of you from different parts of the world, some from the east coast of Australia, some from other parts of the world. So very welcome to all of you. This session that I'm going to be running today is going to be about 30 minutes in duration. I don't want to do all of the talking. So as Carol has said, if you have anything that you would like to share, any thoughts, any disagreements, any questions, you're most welcome to type them into the text messages box on the left-hand side of your screen. And as I go through the slides, I'm hoping that there is enough materials on the slides to help in case English is not your first language. So let's get started right away. Today's agenda, what we're going to be doing today is we're going to be just going through the whole question of rechargeable batteries. Why do we use them? Different chemistries. And then from there, we will segue into talking about lithium rechargeable batteries specifically, asking the question, are they safe? What are the different types of lithium cells that you can get, different sizes and shapes? And then we'll talk about how to select a suitable cell for your project, how to connect them together, charging and discharging, how to manage them, and so on. So the whole session will take about 30 minutes, as I say. So let's get started. And as people continue to join us, you're all very welcome. So let's get moving. I presume you can all hear me okay in your parts of the world. I can see my mic levels flicking, but I can't tell whether you're hearing. So if you can't hear, or if the audio drops out for whatever reason, please let us know or let Carol know immediately. So just a little bit about myself. My name is Simon Chan. I'm the Chief Engineer at Radlink Communications. We're a company based in Perth in Western Australia. I was born in Hong Kong and I've lived in Australia since 1974. So I've certainly been raised and educated here in Perth. I've worked in several cities around the world, and Perth is my home, and I love being here. And what I do love most is that I enjoy research and development and creating new products. I've been in the industry for 31 years now, and I've worked in a lot of very interesting companies over the last 31 years. Right now, I'm working for Australia's largest two-way radio integration company. What that means is that we use digital two-way radios, and we provide that as a critical communication system for companies such as mining companies, hospitals, shopping centers, and so on. So we provide critical communications. And because we have our own energy storage needs, many of our systems are based in remote locations far away from the electrical grid. We've had to look for solutions to provide for our energy storage after dark. And also for many of the mining companies, because we are working in a critical communications environment, we have to make sure that we can deliver power constantly and deliver communications even when the sun is not shining. And so we've been researching for the last or last many years on different types of technology, but only in the last 12 months have we made some significant breakthroughs, and we have started using lithium batteries as our solution. And as we go through this presentation, hopefully you get an idea of why we went down this path, and it may be something that will be of interest to you as well. I'm guessing that from our presentation here today, from our gathering here today, different people will have different things that they want to learn. And so this will be an opportunity for you to ask questions and to share your knowledge as well. So let's move on to the next slide. So let's look at the question of why we use rechargeable batteries. You know, we all use rechargeable batteries in our daily life. I'm guessing that you're possibly watching this webinar from your laptop computer, and you may be using a smartphone. You may even have a tablet sitting next to you. All of these devices require low-cost, lightweight, and long battery life solutions for energy storage. And now, there are different types of technologies to enable you to be able to store energy. But the most important thing is they all have to be low cost, lightweight, and have a good longevity so that you don't keep replacing your batteries every few months. And of course, in this day and age, there's a real expectation that there is a charger on board. Some of you may be old enough to remember the days when rechargeable systems did not necessarily have an onboard charger, and you have to connect an external charger to keep everything ticking over. I guess that's not too different from what we try to do in an electric car scenario, where the car really is a motor connected to a battery, but the battery needs to come back to base for charging. You might also remember 10 plus years ago, charging batteries, rechargeable batteries, was a real challenge, was a really difficult thing. But things are so much easier now because of advances in microcontroller based charging systems. So just for other people who are in the audience today, where and why do you use rechargeable batteries? Do you want to type some of your questions into the screen and I can read them out? Or you're too shy to talk about where you're using your rechargeable batteries? Think of examples where you might need a rechargeable battery. I mean, I've mentioned your laptop, your smartphone, your tablet. I suppose for some people, I've got a watch that has a little solar panel on it, and it uses a very tiny little rechargeable battery, so that I never have to go and get a battery changed out. Correct? Yes. Power tools. Lots of power tools around, and they require a particular type of characteristic in rechargeable batteries, which is peak power delivery. They have to be quick to charge and to be able to deliver lots of power for those few seconds when you're drilling a hole or cutting a hole on a piece of wood or something. Let's think about what currently available rechargeable technologies there are. Okay, we've got Simon here, another Simon, saying that avionic power supply in remotely piloted aerial vehicles. That's correct. And all of these have different demands on energy storage. And the key to the modern power systems that we need to design is high energy density and yet safe, with the ability to deliver peak power when required. And more importantly, they have to be easy to recharge. We don't want systems that are sort of very clunky to recharge. So let's look at lead acid batteries. These date back to the early 1900s. And well, we all know that they're readily available and low cost. You can go into even your local hardware store and get several of the smaller sized lead acid batteries. We still use them, lead acid batteries, in motor vehicles for cranking to start up your car engine in the morning. But unfortunately, lead is a toxic material, and lead acid batteries cannot be rapidly charged. you can't really do a fast charge on a lead acid battery. Typically, they're very heavy as well, and as I've mentioned here on the slide, they're about 30 to 50 watt hours per kilogram. And so if you multiply, say for instance, a 60 amp hour battery by 12 volts, that's a 720 watt hour battery. So you divide it by 50, and you're talking about 30 something kilograms in weight for something which should theoretically be quite simple to carry around. Moreover, lead acid batteries are quite easy to damage. Those of you who are familiar in the critical communication world as I am, we find that we have to change our batteries out every 18 to 24 months, simply because we don't know whether the batteries will survive much longer. So we don't want our critical communication system to fail due to unreliable batteries. Another problem with these batteries is that if you excessively discharge them beyond approximately 80% depth of discharge, which means, for instance, if you've got a 100 amp hour battery and you take out 80 amp hours of storage, if you go beyond that point, there's a chance that you will damage your battery irreparably. And the other thing is that with age, the electrodes can sometimes become brittle, and therefore the battery becomes unreliable. So I don't know whether you've also seen situations where lead acid batteries are bulged or cracked or started leaking. These are all bad things about lead acid batteries. So let's look at the next chemistry. So before lithium batteries came along, there was a lot of nickel-based batteries. There's the early 1950s, we saw the beginning of nickel-cadmium batteries. But once again, nickel-cadmium carries a toxic chemical, cadmium, which means it's not exactly environmentally friendly. I see that Gavin has just said that he has seen batteries explode. I presume he's talking about lead acid batteries. And yes, we've got some batteries in the back here in the workshop which have been struck by lightning, we've been told, and they certainly left a bit of a mess in the communications room where we had to rescue the batteries. Yes, so coming back to nickel-cadmium batteries, they're readily available. You can buy them, you can still buy them, and they're low cost. The best part about them, I think, is that they can be very, very rapidly charged, 1 to 2 hours to get to full charge, and they're able to deliver an incredibly high peak discharge current. So that means if you're using, in the old days of the power tools, they were certainly the batteries of choice. But they have a terrible self-discharge characteristics. I don't know if you've ever left your drill or electric tool, rechargeable tool on the bench and found that the battery has gone flat in the time that you've basically not used it. There's also that problem that many of you know about, which is called charge-discharge memory effect. We won't go into details now, but let's keep moving because otherwise we'll run out of time. Another chemistry that has been quite popular up till recently, and you would have seen them in the early cell phones, in the early sort of portable equipment that we saw, and that's the nickel metal hydride battery types. Low cost, once again, readily available, very good energy to weight ratio, and it was able to deliver good, reasonable amount of peak discharge current. And the best part is there's no discharge charge memory effect. But again, it has a terrible self-discharge sort of characteristic, and it's a very limited cycle life. So you might find only 500 cycles and you need to change them out. And the charging time is slightly higher because of the chemistry. Right, what I've got here is a very, very useful summary from the Battery University. So I want to thank them for giving me the opportunity to quote it. You can turn to that link yourself. The Battery University is a very, very useful resource for those of you who have never found it before, if you want to know more about different types of battery chemistries. But on this particular chart, not the darkened area, I've covered off the summaries of the different chemistries that we've already discussed. Now, it's a case of horses for courses when it comes to battery chemistry, because for a long time, there wasn't a great deal of choice either. Lead acid was used for heavy-duty products, and nickel metal hydride was used for portable equipment. But do you remember the days of your first brick mobile telephone? Or maybe I'm showing my age here. But that didn't really last very long. The battery life on those telephones was quite terrible. But in the time that we've been in the last couple of decades, we've seen amazing advances in science and technology. And so this is where we now move on to the next thing, which is the lithium battery. Oops, it's not supposed to say 1900s, it's actually 1990s. So there's a typo there on that particular slide. So the question that's often asked is, are lithium batteries safe? Now, you would have read in the newspapers and seen on television around Christmas time last year, there was a whole spate of incidents in which this particular electrical toy called the hoverboard caused a lot of angst. Airlines stopped allowing people from bringing this particular toy on board because they had a habit of catching fire. Well, so people became a bit paranoid about lithium batteries. And for me, who has been importing lithium batteries into Australia, we've certainly found all sorts of hassles. I had a shipment of lithium batteries sitting at Shenzhen, which is a port in southern China, and that had been stopped because the authorities were afraid that this container load of batteries was going to go up and take up the whole boat. Now, we've been doing this for a long time, and all of a sudden there were new rules being imposed. And so the question is always, is it safe? Well, I think it's one of those yes and no answers, because the early generations of lithium-ion batteries were really difficult to charge. I don't know how many of you were around when you tried to charge lithium-ion batteries and you found that if you exceeded the end of charge, those batteries got really hot. And because of the high energy and power densities in a small package, we're talking about 5 to 8 times the energy capacity of a lead acid battery in a small amount of material. That can create a big mess when you have a small fault, maybe a short circuit inside the cell or something like that. You could have smoking circuits and burning circuits very quickly. However, if you stick to the design guidelines for lithium batteries, they're actually quite safe. Let's explore this a little bit more. There are 3 particular lithium chemistries that I want to talk about today. The first one is the lithium cobalt oxide. That has been around for a long time. You will see this particular chemistry being used in smartphones, in tablets, in cameras, and it's a very high energy dense material. The upside of this particular material is that it has it's very light. In other words, you can put them into a portable equipment and not have to worry about the weight. In terms of charging, you have to charge it with constant current followed by constant voltage. What it means is that if you've got a cell that's rated to a particular capacity, you need to charge that cell using constant current until the cell's potential difference between the positive and negative terminals reaches a particular value, and at which point you switch to constant voltage charging to finish the charge cycle. I'll explain a little bit more about this in a few slides, but just for now, let's just say that if you were to purchase a 3.6 volt, 2400 milliamp hour lithium cobalt oxide cell, which you can buy on, from different electronic and hobby stores, you can charge that cell at up to 1C. What 1C means is you can charge it up to the same as its capacity, one times the capacity. So that's 2.4 amps. And you can charge it up to 4.2 volts, which is your maximum charge voltage. So what you do is you have a constant current source providing power into the battery at 2.4 amps up to that 4.2 volt limit. At which point you have to switch from constant current, you've got to reduce the current and switch to just constant voltage and charge it at 4.2 volts. These cells that you can buy can discharge it up to 1C, so again 2.4 amps, but you must not discharge them below 2.5 volts, because below that voltage, the cell's chemistry changes and you'll no longer be able to use it. Typically, this particular battery chemistry can be used between 500 and 1,000 times. So not a great deal. If you're doing it on a daily basis, you might be able to get 2 or 3 years out of it. The most negative aspect of this particular chemistry is that at 150 degrees C, the battery has a thermal runaway condition. Now, for those of you who've been involved in power electronics, you will know that a lot of our components, MOSFETs, transistors, etc., they can reach 150 degrees C just in normal operating conditions. And of course, in an overcurrent condition, this will really be catastrophic. This particular battery will catch fire and go up in flames and leave a bit of a mess. And cobalt is not a friendly chemical, so it can leave toxicity issues. Another chemistry that's quite common that you can see is called lithium manganese oxide. Now, this is a 3.7 volt cell. It has a slightly lower capacity than the previous one, the lithium cobalt oxide. It uses the same method of charging, but has a different charging regime. You can charge this battery at up to 3C, which means you can charge it in about 20 minutes. So it's a fairly fast charging battery, 20 minutes plus a little bit extra to make sure that it's reached its capacity. You can discharge it at up to 10C. So it's not surprising then that we use these particular batteries inside our power tools. Things that if you were drilling a hole or cutting a piece of wood, you need the battery to be able to deliver 10 times its rated current at a very, very short time. So in other words, you dump the entire charge from the battery in just 6 minutes. So you might charge it over a 60-minute or 30-minute time, but you use it all in 6 minutes. And so these are being used in high power density products like power tools, medical devices, and electric cars. This one also has a thermal runaway problem. It's at about 250 degrees C. The next chemistry I want to talk about is the lithium nickel manganese cobalt oxide. It's a bit of a mouthful, so we shorten it to NMC, so lithium NMC. It's also 3.7 volts. It's got a bit more energy capacity or density than the previous one, but you can only charge it slowly at up to 1C. You can only discharge it up to 2C. The upside of this particular product is that it has between 1 to 2,000 cycles. So that translates to about 2.5 to 5 years worth of daily usage. So these are good for electric bikes, electric cars. But once again, there's a bit of a thermal runaway problem at 210 degrees C. Now we're coming to a battery chemistry that is very close to my heart. I've spent the last 1 year researching and working with this particular chemistry. It's known as lithium ferrophosphate, or otherwise known as lithium iron phosphate. Not ion as ION, but iron. So lithium iron phosphate. We also call it LFP for short. The nominal voltage for this particular battery cell is only 3.2 volts. So the capacity is not huge, so I would say it's moderate. Nevertheless, in terms of comparison, this particular battery for the same energy capacity is only 1/3 of the weight of a lead acid battery. This is significant. If you were using it in an electric car, for instance, that power to weight ratio is very, very important. Once again, like all lithium batteries, it requires constant current and constant voltage charging. You can charge it up to 1C, so you can charge it at the rated current for 1 hour plus a little bit of extra. And the maximum charge voltage is 3.65, or the maximum recommended voltage is 3.65 volts. However, you can discharge this baby at up to 5C, so you can discharge everything in 12 minutes. In fact, I'm working with our supplier in China now, who can now supply me with a 10C and a 20C battery. So what a 10C battery will be able to deliver all of its load in 6 minutes, and a 20C will be able to deliver all of its load in 3 minutes. We're looking at that, at using that for equipment which need a very high cranking current. to be able to deliver, for instance, the necessary torque and energy to make an aircraft take off from the ground. But once it's reached cruising out, or not even cruising altitude, once it's in the air, we can change battery packs to another battery pack, same chemistry, but a different battery pack that will deliver the current more slowly to keep the aircraft in the air. This battery also has a life of between 1,000 to 2,000 cycles. It is good for high load currents and has great endurance. Now, if you look at that little chart there on the right, it's known as a spider web graph. And the most important thing to me as a design engineer for critical communication systems is the safety aspect. Thermal runaway is beyond 270 degrees C. As I say to my colleagues, if your cabinet is running at 270 degrees C, I think you should leave the room. You shouldn't hang around because something else is going to go up before these batteries. And the other upside of this particular, what we call safe lithium battery, is that it can sustain a moderate amount of overcharging without damage. Recently, we used a solar panel to charge these batteries, but for some reason beyond our understanding, the protection system didn't kick in correctly, and we found that the cells reached over 4.2 volts per cell, and it continued to work. There was no visible damage. Of course, we might not know until the end of its life that it hasn't been able to deliver all of its power for all of its life. For an Australian company as ours, this is a fantastic chemistry because it can sustain high temperature usage. In many of our communications centers, if we don't use air conditioning, which will save us a lot of energy, then we could actually run our equipment at close to 50 or 55 degrees C. And we know that these batteries, the LFP batteries, will work happily up to 65 degrees C. And so, as I said here at the bottom right-hand corner, it's my favorite battery chemistry. Okay, it's just a quick chart here. I won't spend much time on this. You can look back on this when you receive your PowerPoint presentation. You can see how we can compare the different chemistries. The leftmost one is the lead acid, and then you've got the two green ones, which are the nickel-based technologies, and then the orange ones. We've only looked at a couple of those, 4 of those, and basically those are the high energy density lithium batteries. I've got a little graphic here which is helpful for you to grasp how the different shapes and sizes of batteries work. On the right-hand side, we've got a lead acid battery. As you can see in the annotation, it's 7.01 kilograms, and it has occupied a volume of 2.32 liters. That's quite big and quite heavy. In the middle is, as I said, my favorite technology, lithium ferrophosphate. It is 2.63 kilograms. So it's about a third of the weight, and it takes up just a little bit more than half the volume of the lead acid. And then the lithium cobalt oxide on the leftmost side is the 1.65 kilogram with 0.86 of a liter volume that it occupies. The challenge with the one on the left is that it has a temperature issue. Okay. Again, I just want to now show you the full charts that the Battery University put together. You can follow that link later on when you get your presentations in your inboxes. Now, there are different types of lithium battery cell shapes and sizes. For the ones that I use, the lithium ferrophosphates, we can get them in all 3 sizes. The 18650 derives its name from the fact that the diameter of the cell is 18 millimeters and the length of the cell is 65 millimeters. And you can extrapolate that to the 26650 and the 32650. Now, the 32650 is a fairly new cell, and not too many companies are carrying it at the moment, but you can certainly buy them. If you need assistance in sourcing these batteries, talk to me afterwards, and we can go and I can show you some of the tier 1 suppliers that we have already found. Just note also that the photos that I'll put on this particular side are not to scale. Okay, so the top one is not as long as it looks. Okay, selecting the right cell for the job is very important. And the first question you need to ask is, how will you connect all your cells together? Now, the next question you need to ask yourself is, what is the nominal operating voltage? Because that tells you how many cells you need to put in series to achieve your nominal operating voltage. And then the next question to ask is, what's the required amp hour capacity? What is the total number of amps you need to deliver multiplied by the number of minutes or hours that it needs to run? And then you have to work that out by working out how many cells you need to put in parallel. Unlike a lead acid battery, which already has all the cells integrated inside, with a lithium battery solution, you actually have an incredible flexibility of being able to make anything you want. We've created some really novel batteries for caravans and so on, which are very flat for hiding behind panels and so on. But again, the same principle applies. What is your operating voltage and how many amp hours do you need? Okay, let's look at this worked example here, because I think an example probably will explain it a lot better. Let's say you're building a scooter, a little sort of you know, not the toy scooters, but something a little bit bigger. You need a 36-volt operating voltage with a 90 amp hour battery. So you're looking at something that will run around town for a little while. And so the nominal operating voltage is 36 volts. So what you do first is you divide 36 by 3.2. That tells you you've got 11.25 cells. The question is, do you go higher or lower? Now, some circuits you can't go higher because if you use an excessive voltage, you blow the circuit up. But in the case of an electric motor, yes, you can have a higher voltage. So we've chosen to use 12 cells in series, or 12 banks of cells in series. Okay. Next thing you need to ask yourself is, all right, I've got a 90 amp hour requirement. I've got all these different cells that I can buy from the marketplace. What do I want? So you have to ask yourself the question, is there a size restriction? Is it something thin that you need to make? If that's the case, then you need to go to the 18650. Is it something that has very little size restriction? Well, in the case of a scooter, we've got the space, so we've decided to choose the largest cell available, the 32 millimeter diameter cell, 65 millimeters in length. Not only that, the largest size also allows you to have a higher charging and discharging rate. So you divide 90 by 5 amp hours, which is the 32650 cell that I've got here, and the calculation tells you you can have 18 cells in parallel. All right, let's summarize. So you've got 12 cells in series. That is equal to 38.4 volts. Now, how did I get that? I go 12 times 3.2, and I get 38.4 volts. That's your nominal voltage. What's the minimum voltage? What can we run this thing down to? Well, because it's a lithium ferrophosphate battery, it will allow us to run down to 100% depth of discharge, which is quite amazing. But we know that 100% depth of discharge is achieved or is reached when the voltage across the battery, across the cell, drops to 2.5 volts. So you've got 12 cells in series multiplied by 2.5 volts. That gives you 30 volts minimum. So that means your scooter motor needs to be able to operate down to 30 volts. What's the maximum voltage? Well, if you've just finished charging the cells, they would be hovering at around the 3.65 volt mark. There are 12 of them, so that will be 43.8 volts. So you need to make sure that your scooter motor can take 43.8 volts maximum voltage. As we said earlier, 18 cells in parallel, that comes to 90 amp hours. That's 18 times 5 amp hours to give you 90 amp hours. What you now have is a matrix of cells which are made up of 18 cells in parallel joined together in 12 segments. So there are 18 parallel cells, and you make 12 of these and you join them in series to give you a 12 by 18 matrix. So this is where the shorthand comes in the little line at the bottom. 12S means 12 in series. 18P means 18 in parallel. The 32650 refers to the size of the cell. The 3.2 volts, 5,000 milliamp hours describes the cell. So that's battery pack that we've just made in the last 3 minutes is known as the 12S 18P 32650 3.2 volt 5000 milliamp hour battery pack. Okay, just let's have a look at the characteristics of the cells while we're still talking about chemistries and so on. You notice how flat the discharge characteristics of that cell is. If you compare this with a lead acid, this will beat the lead acid hands down. Basically, from the moment you take it off the charger, all the way right to the very end, because this is a 3200 milliamp hour graph that I've got there, you're probably at 3100 milliamp hours before the voltage starts dropping, and it drops very, very rapidly. We have to stop the discharge at 2.5 volts. That's the end of the pink line that you see there. Let me see whether I can get this thing to work. This is the termination voltage. I don't know whether you can see my finger pointing to it. And when you're charging, you charge it at constant current up to the end of its charge, which is at 3.65 volts. Okay. Let's just move to the next slide. Okay, it's just a couple of things now before we wrap up, because I know I've run out of time. I work very, very closely with my factory in China. As I mentioned, they're a tier 1 company, so they only make cells that are very, very high quality. They sell them into the aerospace, medical, as well as defense type projects. For us in the mining and telecommunications industries, we want to use them because we know that when they say they're giving us a cell with a particular capacity, we can trust them. And so what you have on the top right-hand slide here is the cells as they come off the production line. And so what happens is, you can't really see it in this particular presentation, but we can zoom in later on. Basically, they come out with 2 tabs, a positive and negative terminal. And that then gets put into a case, a steel case, and then you wrap it around with either paper or plastic to turn it into a battery cell. And then the last step, you know how in the last little bit we talked about joining the cells in series and parallel? Well, this is a battery pack. Of course, it's not as big as the one I've just described. What you have here is a bunch of cells connected in different configurations. I don't know whether you can see it, but in here you can see the cells are joined in parallel. And then there are some wires and it connects them in series and so on. We'll have to do this on another session when we can actually zoom in on that. But you just have to trust me for now. Okay, what sort of charging current? Let's just move on. What sort of charging current can we deliver to this battery pack that we've just made, this 36 volts, 90 amp hour battery pack? Well, we know that the 3650 cells can be charged at up to 1C. In other words, if it's 5 amp hour cells, each cell can be charged at up to 5 amps. The recommended charge rate, if you don't want the cells to get too hot, is to charge them with C on 3, which means you charge them over 3 hours. So for a 90 amp hour battery, you divide that by 3. So 90 divided by 3 gives you 30 amps. So what it means is you can fully recharge your little battery pack inside your scooter in 3.5 hours, or just short of that. Or if you want to do overnight charging, then you can charge it 10 amps for 10 hours. Okay, and that's the constant current charging, the CC charging. And then you've got to switch to the CV charging mode, which is the constant voltage charging mode. You set that at the threshold of 43.8 volts. You might remember a few slides ago we talked about the fact that 43.8 volts is the maximum voltage allowed for this pack, which is we'll go back. When you go through the slides, you'll see how I've done the calculations. But basically, your power supply must not exceed this value. So you say, for instance, if you're building a 10 amp power charger, then you have to have a 10 amp capable current source with a voltage limit of 43.8 volts. Right, what about discharge? What sort of currents can we get out of this pack? Well, the amazing thing, of course, is the 32650 cells can be discharged at up to 5C, so 5 times its capacity. Since you're on the amp pack, you'll be able to deliver a 450 amp starting current. that's going to make you do wheelies on your scooter. Okay, and once you reach your velocity or the speed that you're trying to achieve, you can the current will drop right back, and you can operate at up to 1 C for 1 hour. So you can continue to discharge this pack at 90 amps for 1 hour. But I would suggest that if you were running a scooter, once you've once you've actually got past your inertia stage, your battery current will be significantly lower than 90 amps, probably only 20 amps even. So your battery will last easily 4 hours or more. So the important thing about this whole exercise is we've been talking a lot about current, and those of you who are electrical engineers or technicians, you will know that there's a thing called I squared R heat losses, or heat generated by I squared R. When the current is squared multiplied by the resistance of the current that's flowing through that resistance, that causes heat to be emitted. So you must make sure that whatever connectors you use, they're fit for purpose, because you have got a 450 amp peak current and up to 90 amps of operating current. Okay. Next, now I was at the Chinese battery factory only a few weeks ago because we were manufacturing some battery packs, and I use a FLIR camera for all of my diagnostic stuff. What we have here on the right-hand side is you can see the cells underneath the plastic case that we've got. They're glowing because they're warmer. So the black areas are cool. The yellow areas, the brightest yellow areas, are the hottest part. Now, the room that I was working in is temperature controlled and humidity controlled at 25 degrees C. Now, this battery, even though it was working at 1 C, was only operating at 34 degrees C. So it was only just about 10 degrees higher than ambient. But where we have problems, as you can see here, is where the battery management system interconnections are taking place. That's a little bit too warm for my liking. You can see the cables, the power cables that go out to the load. I think they're a little bit undersized. So it's important that whenever you do design with batteries, that you have access to good quality test equipment. And I use a FLIR camera which plugs into my iPhone, and I can take videos and stills very, very quickly for later analysis. Now, this is the circuit breaker that we're using for this particular design to make sure that even though we've got battery management systems and the works, the circuit breaker will still click in and kill the circuit in the event of a sustained short circuit or for instance, the battery management system might fail. The circuit breaker is actually running warmer than the battery. As you can see, it's 39 degrees C. So there's always a need to make sure that there is enough space for the heat to escape in your design. Now, battery management system, I mentioned it quickly just now. Battery management system, or the BMS, is your insurance policy. Now, it protects against misuse and abuse. I don't know about your customers. Ours often don't listen to what we tell them. They misuse and abuse the batteries that we supply. One of the things that they do is the chargers that they use are not specified correctly. So there's an overcharging scenario. So the BMS protects the individual banks of cells from overvoltage. They also stop the cells from discharging when it reaches the 100% depth of discharge mark. Not only that, if there's a sustained overcurrent condition, excessive continuous current, the BMS will also kick in. There's a short circuit protection for instantaneous faults generated by a short circuit. And of course, there's the over temperature set to 65 degrees C. So 65 degrees C is way above ambient in most cases. And that can only happen due to incorrect usage. Maybe the batteries have been placed too close to a heat source or some other thing. The BMS monitors each parallel bank of cells continuously for fault conditions. So that's your insurance policy. What sort of battery life can we expect out of an LFP battery? Well, here is a chart showing a 26650 cell, 3200 milliamp hours, and we're discharging it continuously. We're cycling it every hour, basically. We charge it for 1 hour, discharge it for 1 hour, and we keep doing it. And the specification sheet from the supplier says that it will achieve better than or equal to 2000 cycles At 100% depth of discharge, the residual capacity is no less than 80% of rated capacity at 1C rate after that 2000 cycles. So at 2000 cycles, which is where my finger is pointing, you can see that unfortunately this graph is a little bit too small for viewing, but basically what we're saying is that at 2000 cycles, we still have 90% of the original capacity left. Imagine if you were trying to provide a battery for something that's being used daily. You'll be able to run that thing for 5.5 years and know that at 1C charge and discharge, you will still be able to achieve 90% residual capacity. That is amazing. This is what the difference between buying from a tier 1 supplier and some other supplier. They've got the stats to prove it as well. They've got test jigs that have been running for the past few years. I saw some really dust-covered batteries that have been charged daily, just like this one, that have been running continuously since year 1 sort of thing. The other amazing thing with the LFP batteries is that if you look after them, just like you look after a lead-acid battery and don't allow them to discharge below 70% depth of discharge, you can expect about 6,000 cycles of charging and discharging. That's over 16 years of daily charging and discharging. Fantastic if you're in the solar industry, because, well, I suspect the solar panels would have aged much faster than the batteries. But of course, you need to design it in such a way that your system doesn't go below 70% depth of discharge. Only a few more slides and then we're finished. Now, disposal and recycling, many people ask me about this. Now, while LFP cells natively do not contain any toxic chemicals because the active ingredient is lithium, and then you've got the ferro, which is the iron, and then you've got the phosphate. Both the iron and the phosphate will actually biodegrade. Nevertheless, unplanned disposal in Australia is still a concern. What happens is very many people don't even flatten the batteries before they chuck them in the bin. So the batteries, if they were crushed, they would short circuit, and there's a risk that if the cables are too thin to which the thing is connected, there's a risk of overheating and then a fire. And of course, we're talking about LFPs here, but other lithium chemistries that we mentioned earlier, like the cobalt or the manganese and so on, they're even worse. They do leave behind some residual toxic chemicals. Recycling batteries in Asia is one option, and we offer that to our customers. We will get them back from them, and we will ship them to China to be properly recycled. But here is an opportunity for those of you who are entrepreneurs, because I think this is an opportunity for Australian businesses to get involved. Okay, in summary, you must be happy that we've got there. Sorry, it's taken 45 minutes. It's a bit longer than I had planned. Lithium batteries have been around for 20 years, but the rates of adoption only took off after smartphones became a commodity. And you can see that in all the growth, the market projections and so on. It is an amazing industry that we're looking at. Because of the proliferation of electric vehicles and solar PV, solar photovoltaic systems, people are looking to store energy. There are new requirements, new opportunities every day. In a radio company, we've actually spun off a whole new division just to do this. The demand for lightweight, long life and low cost energy storage solutions is going what they call gangbusters. Everyone wants it, and different people in different places want it. We've got even heavy demand from the recreation market, which is people who want to go camping and carry a lightweight battery around to keep their phones alive and so on. So I personally believe that smart, networked and managed LFP-based battery solutions have a very bright future. And so I want to thank you for listening, and I hope that you will want to participate at this point. It's your turn now. If you've got any questions, please pop them in the text messages box. I don't know how to hand the microphone around, so Carol, I'll have to leave that to you. If you've got complex questions or wish to exchange ideas, you've got my email address there. Please don't abuse that. I really want to be able to even set up a little working group if people are interested. Maybe we can meet together like this, use this particular platform. We'll borrow it from EIT, and we can have an opportunity to chat every 2 months in a forum which is fairly laid back like this to exchange ideas. So over to you. Any questions? I'll click the stop talking button now, Carol, so if you would like to take over.
Okay, if anybody has got any questions, just put a message in the text box, or beside the push to talk button at the bottom, the red button, there is a hand to the right of it. So if you click on that, that will raise your hand, and then I'll know that you want me to hand the microphone over to you. The one important thing, if you do use the microphone, is you have to click on the red button to start talking, and then you need to click on it again to release it to us. So if anybody's got any questions, either put them in the text box for Simon, or if you raise your hand, and then we can pass the microphone over to you. We are recording the session, so you will receive a copy of the recording in about 2 weeks' time, by the time, and it will be uploaded onto YouTube. So I'll pass the microphone over to you.